Fine, guys, let's start. Okay. So, in last class, we have seen point estimate. Fine. So, we have seen what is a point estimate and few point estimate examples like sample mean could be a point estimate and sample proportion also could be a point estimate. Okay. So, just to give you a small recap, what is a point estimate, guys? Point estimate is that particular parameter, okay, from the sample which will try to represent the population parameter. Agree? If population is having a, we are having a population, we are taking a sample from that. Okay. Now, a particular measurement of the sample which will represent the corresponding measurement from the population. Okay. Can be called as a point estimate. Fine. So now, as I said, we are going to see one of the most important theorem called as central limit theorem. Okay. But before that, there are just two words you need to understand, okay, which are called as parameter and statistic. Okay, so in statistics, okay, in statistics, parameter and there are two words, parameter and statistics, which are very simple. So anything related to the population, okay, is called as parameter. Okay, that means population mean, population variance, population standard deviation. Okay, all these are called as parameters, guys. Anything related to sample is called a statistic. Statistic mean, okay, statistic variance, population, etc. Agree? So these two terms we need to remember. Okay. Now, once we understood these two terms, we'll now try to understand what is central limit theorem. Okay. Fine. So now see, guys, what's the point over here? Let's try to understand. See, now the central limit theorem states that the distribution of the sample means of a large number of independent and identically distributed random variables will approach a normal distribution regardless of the underlying distribution of the variables. Okay, so definition thoda lengthy hai, okay, but concept is very simple. Fine, let's try to understand it in very simple words. Okay, see, guys, as I said, central limit theorem is one of the most important theorem. Okay, and before central limit theorem and after central limit theorem, there were so many changes in the statistics, because once they have discovered this theorem, fine, so their work has become very easy. Why? We will try to understand. Okay, see, first of all, the main crux of the theorem is this. The theorem is saying, see, now till now, what was our mindset, guys? Our mindset was, first of all, we will have a normal distribution. Okay, if you have a normal distribution, straightforward, we are happy. Agree? If we don't have a normal distribution, what we are trying to do? We are trying to convert it into a normal distribution. How we are going to convert it into a normal distribution? By doing some transformations. Okay, by doing some transformations, we are trying to convert it. Okay, this is fine. But the main problem arrives when in real life, okay, when you are working on very large data sets, okay, it might be impossible to convert that into a normal distribution, no matter what transformations you apply. Okay, so if your distribution is like this, okay, I don't know what is this distribution. Even though you do any sort of transformations, most of the time in the real life, the data set will be extremely skewed or distorted, or we don't know, it will not be a normal distribution, fine. And it is also very difficult to apply transformations and bring it into normal distribution. Agree? So in these difficult times, central limit theorem will come to our rescue, and this theorem states that, observe carefully my words, no matter what is the underlying distribution of population? Okay, the sampling distribution. Okay, see, before that, we need to understand sampling distributions. Okay, so I think we have discussed it yesterday, but I will tell you. See, sampling distribution is, see, you are having a, let's say you have a population, guys. Fine, this is population, whole data. In from this, you, something, there is something called a sampling distribution. Sampling distribution means creating a distribution by taking different samples. Okay, that means you take one sample. This is sample one. Okay, sample two, sample three. Okay, like that, you took sample n samples you took. Okay, now this became sampling distribution, guys. Okay, you got a new data set. Okay, distribution is point of data, sorry, collection of data. Okay, so now you are having a new data. What are these are samples. Okay, different samples from the population. Now our central limit theorem says no matter what is the distribution of this population, okay, the sampling distribution samples, okay, the sampling distribution samples, that means these samples, okay, their mean, okay, their mean tends to approximate a normal distribution. Okay, sampling distribution mean, that means each sample will have a mean. Fine, that means it will have, let's say, x1 bar. Okay, this will have x2 bar. Okay, like that, xn bar. Fine, the mean of these will approximate a normal distribution is the theorem. Okay, simple words, in I will explain once again. See, the theorem will say, irrespective of the distribution of the population, if you take sufficiently large, okay, if you take some decent number of samples from each of this from this population, okay, these are n samples, and if you calculate the mean of that samples, okay, each sample will have mean. Sample is what, let's say this population is having 1 crore points. Okay, from that you are taking 1000 points each sample. Okay, this sample is 1k 1k 1k. Okay, this is 1k 1k 1k. Fine, so this sample one you took 1000 points. Okay, the further 1000 points, there will be mean, let me call it as x1 bar. Like that, s2 points, another set of 1000 points, it will also have another mean. Okay, like that, you took, for example, let's say 30 samples. Fine, so this 30 samples, okay, you took, and then you will have 30 means, sample means. Fine, you will have sample means. So according to this theorem, these sample means will follow a what, normal distribution. Okay, the sample mean will follow a normal distribution. Getting? Fine, and the mean of this sampling distribution, okay, the mean of this sampling distribution, this is a mean of each, this is a set of means. What are these, guys? X1 x2 x3, all are these, all these are means of this sample. Okay, mean of this individual sample. Now the mean of these samples, okay, the mean of this, mean of x1 x2 xn bar, okay, will be almost same as a population mean, which is mean. Okay, is it clear, guys? How many people did not understand? Tell me.
Can you please repeat last lines? Mean of all.
See, okay, see, first of all, there is a population. We are taking sufficient samples, okay, and the samples got created. Are we good till this point? Let's go step by step.
Yes.
Okay, we are good. So we took 10 some a number of samples. Each of these sample will have a mean. These are it means.
Yes.
Okay. Now the game is with only these means. X1, X2, X3, X bar. These means, what are these means of the samples? Or these are also called sample means.
Yes.
Okay, fine. Now, simple. Central limit theorem will say, first point, the sample means, okay, the sample means, or this is also called sampling distribution, okay. This sampling distribution, okay, this means, okay, sampling distribution means, okay, to be specific, it will follow a normal distribution because these are just points, some 30 points. If you plot them, they will follow a normal distribution is one point. Second point is mean of the sampling distribution. Okay, this mean, these are just 30 points, right? These 30 points will again have a mean.
30 means you mean?
No, only one. This is one single point, right? For
Yes,
example,
yes, yes.
this is
X1,
1000 points. This
X1
1000
is
point.
having
Hmm?
X1 is having X1 mean. X2 is having
No,
X2
no,
mean,
no.
right?
X1 is what? It's 1 point. See, that's what I'm saying. See, here you are having 1000 points. From 1000 points, you took this sample. Sample inside this S1, how many points will you have? Tell me.
30 points. I mean, 1000 points.
1000 points. Okay, just wait. 1000 points we're having. And you will do a mean of that average value.
Yes.
Oh, what is that? X1
X1,
bar.
X1, X2,
X1
X1 bar.
bar.
Yes.
Okay. Now, X1 bar is how many values?
1000 values.
Why? For 1000 values, you are calculating average. The average will be again 1000 values.
Oh, it's only one. Yeah, sorry.
Getting? So
Mean.
if
Yeah, yeah.
S1 is like, let's say 1000 values, the average
Yeah.
of these values will be what? One value or 1000 values?
One value.
One value, and that one value is X1 bar.
Okay.
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 Now
Hmm.
S2 is also 1000 values. Average of this will be one value, X2 bar.
Hmm. X, yes.
Like that, Xn bar. Okay. Now you have 30 values, 30 individual single values. Yes.
Yes, yes.
And for these 30 values, again, you can have one mean.
Okay, we are summing up and averaging by 30.
Yes. Yes.
Okay. Okay, then we are getting mu.
No, no, no.
No, no. Okay, fine. Mu.
Mu is a population parameter. Okay. You will
Okay.
have a mean of the sample mean. That is called mean of the sample mean. What are these? These are sample means. X1 bar is a first sample mean.
Yeah,
X2
got it.
bar is second sample mean.
Yes.
Like that, this whole X1, X2, X bar is what? It is a sample means.
Yes.
Okay. Now it will say the sampling means if you plot, it will follow a normal distribution is 1 point and mean of the sample means. Now these are 30 points. So again, you can calculate a mean, sum all of this by 30.
Okay.
Okay. That value will be almost equal to the population mean. Okay. The mean of the sample means. Okay. Mean of the sample means. Fine. See, mean of the sample means. Now, in this line only, you can understand everything. First of all, mean of the sample means. Sample means what? Each sample mean. So that means you need to take all samples. You are taking all samples S1, S2. And for each sample, you are calculating mean X1, X2, X3. Like that, you got 30 means. Okay, now this became sample means. Because now these are again one set of data. 30 means, it could be means, it could be heights, anything. But there are 30 points in this data set. Okay. Now again, you can calculate a mean of that. That will become mean of the sample means. Okay, that mean of the sample means will approximate the population mean. What is the population, actual population? Okay, and this sample means will follow a normal distribution when plotted. Is the theorem clear, guys?
Yeah, Santosh.
Yes, sir.
Okay. Mhm. Fine. Everybody, it's clear, right?
Yes.
Okay. Now the main important point is this will true. This will be true irrespective of the population distribution. Okay, that is a point. Irrespective of the population distribution could be anything. I don't know population. What is a population distribution? Population distribution could be this one or this one, anything, whatever be the population distribution. See, our goal, as I said from past few classes, our goal is to work on normal distribution. We want to have normal distribution. So why this is theorem is magical? Because it is saying whatever be the actual population distribution, I don't know. He's saying you're taking height. Okay, even if you are able to collect the height of complete population of India or complete Telangana population, it will not be a normal distribution. Okay, it will be some sorted distribution. Okay, but that's fine. What it is saying, whatever be the population distribution, irrespective of that, if you take sufficient samples, okay, if you take sufficient samples, and for each sample, if you calculate the mean, okay, take the samples and calculate the mean. Okay, now this will become sample means. Okay, now that sample means, fine, that sample means always try to follow a normal distribution. Okay, always try to follow a normal distribution, and mean of the sample means will always be equal to the population mean. Okay, isn't it interesting and wonderful? Because it is giving us two things. One is our goal to work on the normal distribution is getting satisfied, because it is saying if instead of working on the overall population, if at all each of the sample is what, each of this sample is representing a it is trying to represent the population. Okay, like that, if you're taking 30 points, you will have 30 different samples, and each of, and this mean is again what, when you're, whenever you're taking a mean, what does that mean? It is trying to represent that particular data. Okay, see, as I said, if in a class, if there are different types of people with different heights, okay, right, starting from 4.2 to some 6, okay, now we don't consider all of them, right? We'll ask what is the average height of the class. Average height of the class, well, let's say if it is 4.8, what does this mean? This 4.8 is representing the overall heights of the class. Similarly, here when I say x1 bar, this x1 bar is what? X1 bar is the mean of this first sample. Okay, mean of this first sample. So this sample 1 is getting represented by x1 bar. Now x2 bar is representing the sample 2. Okay, like that you are having, like that we are having all the different means which are representing the, which are representing its samples. Fine. So now theorem is saying if you are not able to work on the whole data, just take the samples and take the means. Okay, this means, okay, this means will, if you plot, this means will plot, will be following a normal distribution. Okay, so you can work on this. Now, since this is normal distribution, right? So obviously you can do what all you want to do, apply all the rules of the normal distribution which you have studied. Okay, and also the mean of the sample distribution, the mean of the sample distribution is approximating what? Population mean. That means again it is also saying obviously you cannot collect overall population data, okay, and find out the mean. How you will get the actual population mu, guys? Actual population mean, collect the complete population data and divide by the count. We cannot do that, obviously. So it is saying even though you are not, you, if you're not able to calculate the actual population mean, that's fine. This the sample means whatever you are having, right? You do the mean of that. Whatever the value you are going to get, that will be approximately equal to population mean. That means it's not exactly, but almost very similar to the population mean. Fine. So that means indirectly you are able to find out the population mean also, even though you don't have the complete population. Fine. Again, see, mean is what? Mean is one thing which will represent the population. So just like how x1 is representing s1, guys, how x2 is representing s2. Okay. Now, which will represent the population? Its mu will represent the population. Agree or not? Population parameter mu, which is a population mean, will represent the population. So this mean also you are able to get just by doing the mean of these samples. Okay, that is the importance of the central limit theorem. Okay, see, I'll just go to definition. Might okay, see, in the study of probability theory, the central limit theorem states that the distribution of sample means approximately normal distribution. Okay, distribution of sample means, okay, as the sample size becomes larger, assuming that all the samples are identical in size and regardless of the population shape. Okay, see, central limit theorem is a statistical, and now you might get doubt. Okay, how if you take random samples and if you take the means of that, how it will follow a normal distribution, and how its mean will be equal to the population parameter mu. It is possible if you take sufficiently large. You cannot simply say, I'm taking two samples. Okay, I will consider only two values from it, and that is one sample. Three values from it, that is one sample. Okay, and then if you are calculating mean of this, that will not be working. Okay, that's why you should take sufficiently large. That means usually the samples extracted should be bigger than 30 observations. That means in each sample, okay, in each sample it should have at least greater than or equal to 30 samples. Okay, 30 samples you need to take. Okay, so it is saying statistical theory stating that given a sufficiently large sample size from a population with a finite level of variance, the mean of all samples from the same population will be approximately equal to the mean of the population. Getting this is the point. Mean of all samples, okay, from the same population will be approximately equal to the mean of the population. Furthermore, all the samples will follow an approximate normal distribution pattern with all the variances being approximately equal to the variance of the population. Okay, the samples will try to follow a normal distribution, and mean of the samples, okay, mean of the each of the samples will all approximately equal to the mean of the population. Okay, so I'd like to show you. Yeah, what is this guy is trying to say? You see, many statistical procedures assume that the data follow a normal distribution because the normal distribution has very nice properties like symmetry and having majority of the data clustered within few standard deviations of the mean. Okay, this is our goal, right? So many times we also want to follow normal distribution. Why? Because it is having properties like symmetry, and also majority of the data is clustered within few standard deviations. What it is saying, it is talking about the empirical formula. Okay, 3 standard deviations, 2 standard deviations. Okay, but unfortunately real world data is often not normally distributed, and the distribution tends to be sample tends to mirror the distribution of the population. Okay, see, distribution of the sample tends to mirror means what? Reflect the distribution of the population. Okay, this means a sample taken from the population with a skewed distribution will also tend to be skewed. Okay, that's what it is saying. See, you are having a population. If you want to take a sample, the sample tends to mirror the distribution of the population. That means whatever the distribution you are having, the sample will also usually have that. That means if you're taking a normal distribution, sample will be normal distribution. If you have a skewed distribution, sample will also skew distribution. Okay, if you have uniform distribution, sample will also be uniform distribution. Okay, skewed will also have skewed. Okay, so just by taking single sample, it is not working. Fine, but what's happening if you take multiple samples? Okay, if you take multiple samples from this, fine, and calculate the mean of all these samples, fine, that mean will follow a normal distribution, guys, not the samples actually. Okay, I'm not sure if you're getting it very correctly. Okay, so see, population, sample 1, sample 2. Okay, don't, if you are having just any doubt, get it clarified in this step. Okay, sample 4. Okay, like that, sample 100, for example. It is just sample. Each of the sample will have 1k points. Okay, now this will have one mean, x1 bar, x2 bar. Okay, like that, x100 bar, guys. Okay, these are sample means. Okay, these are sample means. These are just samples. Okay, now this will, this now the game is with this. Okay, now these are just samples. These are its means, sample means. Okay, now it is saying the sample means will follow a normal distribution if you plot, and the mean of this, mean of the sample mean will be approximately equal to the, this population will have its mean, right? That is called mu. Okay, this mean of the sample mean will be equal to the population mean. Okay, this is the actual concept, and this is irrespective of, this is irrespective of population distribution. Okay, any population distribution, this could be anything. Okay, this is a whole picture of the central limit theorem, guys. Is this clear? It should be very, very clear. Any, there are any doubts? Okay, just Meghana, can you just once repeat the theorem according to you, like what you understood?
So from whole population, we'll take some samples.
Okay,
We find mean for each sample.
mean for each sample. Okay,
Yes. And if we plot that means, we'll get a normal distribution.
okay,
And the mean of those means will be equal, will approximately equal to the mean of total population.
perfect. And what is the advantage of this, Meghana? Why it is very important?
Because in normal distribution, there will be symmetry and we can plot it in less standard deviations.
Perfect. Perfect. Okay, and that is one point. And also, you're also able to find out the population mean. Okay, you're also able to find out the population mean. Okay, this is also one more important point, because if you ask me, hey, what is the actual average height of whole boys in Telangana state? How will I know? I cannot find out, right? So instead of doing that, what actually, how to find out? See, actually, మనకి కంప్లీట్ తెలంగాణలో బాయ్స్ హైట్ యావరేజ్ కావాలి అంటే ద పర్ఫెక్ట్ వే, the if you want 100% exact value, I should go to each and every person, every boy, and find out its height and sum all of that and divide it by count. Okay, but I cannot do that, nobody can do that. దాని బదులు ఏం చేయొచ్చు? Go to different states. Okay, how many states do we have? 30, 29, 30 states. In each state, take some 1,000 people. That I can do. 1,000, you take samples. Okay, heights, each from, let's say, in Telangana, oh, in how many districts do we have? 30 districts, I think, right? Okay, so let's say Rangareddy, for example. Okay, this is Nizamabad, Mahbubnagar, Sirsilla, like that. Okay, all 30 districts you have visited and collected 1,000 boys heights. Agree? After that, just take mean of those, all those sites, 1,000 points mean, 1,000 points mean. Okay, like that you will have 30, what, how many districts you take, those mean. Now this is again one single data set. X1 is just one value, X2 is just value, but here S1 is a collection of 1,000 points. That point should be clear. Okay, S1 is a sample, X1 bar is just a mean. This is one dot, one single point. Okay, this is like that, you are having 30, okay, different values. Fine. Now if I just do the mean of this, okay, if I just do the mean of this, I'm getting what? I'm getting the population mean. That is magic here. Okay, because I did not visit every person, every boy in Telangana state. Okay, I just visited only few points. Once I visited this, sitting at home, I just calculated this and I just did the mean of this 2 minutes mathematical calculation. Whatever I'm able to get, that is actually the population mean. What I should get, that I'm getting directly over here. So I can approximate, okay, that this, all these are actually representing the population. Because see guys, did you understand by now that any distribution is what? Any distribution is just it's mu, okay, and its standard deviation. Just with these two parameters, with these two parameters, we can find out what is how does this graph looks like, right? So what if you observe many a times, we actually don't know the actual distribution, but we only know the mean and its standard deviation. Okay, even in the light bulb example also, he was saying light bulb average is this much and its standard deviation is this much, etc. But we don't know the overall data, right? So the for any distribution, mean and these parameters like standard deviation, variance, those are important. Okay, so that very important parameter of the population we are able to get from our sample means without doing the complete work, just doing the small work, you're able to get the actual population parameter, which is very, very important. Okay, is that clear, Sirisha? Okay, fine. So I hope that is clear. Okay, fine. So we'll try
Simple
to.
sum.
Hmm?
I have one doubt.
Mm-hmm.
So is there anything like do we need to do these many number of samples? Like, is there any condition or as many as possible? Like,
Yeah, you need to be I mean it should be not very small. Okay, it should be somewhat greater, as long as many as possible. Okay, there is not any fixed part, but the only point is if you keep on increasing the samples. Okay,
okay,
if you keep on increasing the samples, obviously you will have a better normal distribution, and also this whatever the sample mean which you are getting, right, that will be more and more closer to the population mean.
okay, okay,
The difference will be more and more less if you're increasing the sample size.
okay,
Okay,
yes, okay, fine.
okay. Now over here, okay, over here in the sample in the okay, so there are only few just conditions. See, as you see, the sample size is large enough. Okay, the few conditions for the central limit theorem to hold true are simple. The sample size is large enough, typically greater than or equal to 30. Okay, that means each sample size should be greater than or equal to 30 values. Fine, and the sample is drawn from a finite population or infinite population with a finite variance. Okay, the population whatever you are getting, right, so that should be a finite population. Okay, or it should have at least a finite variance. Okay, that means you cannot say the population should not be infinite, like the population could not be okay. I would say some infinite count, like let's say stars. Okay, you cannot say the stars in the galaxy if you're trying to calculate something. So first of all, you don't know the complete population range, right? So from where it is starting, where it is ending, you cannot find out. So when you don't know the population parameter itself, how can you like predict on its sample? Fine. First of all, the population which you are trying to consider, that should have some finite. Okay, and the random variables in the sample are identical distributed. That means whatever you are taking from the sample, right, so those should be a bit of identical. That means all the samples should be more or less the same. That means in one sample you cannot take three samples. Okay, in one sample you cannot take just 3 points, and other sample you cannot take 20 or 30. Okay, more or less it should be similar, and also there should be you should be picked from different positions. Okay, for example, if you're taking a sample over here, there should be less overlapping, guys. You cannot just say, okay, one more sample is this, okay, one more sample is this, one more sample is this. Okay, that will not serve purpose. Okay, so it should be, the sample should be identical. That means different from each other, but have same size. That means 30 from here, 30 from here, 30 from here. Okay, 100 from here, 100 from here, 100 from here. Okay, like that. So that because if you cover different portions of the population, so obviously you can have the overall idea. If you concentrate only one particular region, so obviously it will be biased, right? So these are simple rules how to do the sampling distribution. That means how to create the samples from the given uh, population data set. Okay, so once these simple conditions are followed, so whatever you able to take the sample means and do the concepts, you are going to get these two important things. Okay, so now once you have this, okay, so here one thing you need to remember over here is, see, let me check. See here, the population what we are saying, right? So it will have the population parameters will be mu comma rho square, guys. If the population parameter will mu and rho square, okay, what is this mu? Mean. Rho square is what? Variance of the population. And in the sampling distribution, okay, the sampling distribution, okay, the sampling distribution will have mu Okay, because it is almost having this one. The mean, this is a sampling distribution. Okay, the mean of the samples. Okay, mean of the samples, it will have mean almost equal to mu. Okay, and its variance will be population variance by n. Okay, now n is a sample size. Okay, n is a sample size. That means in each sample, sorry, how many samples we are taking? Okay, how many samples we are taking? That is a sample size. Okay, so if the population is having the mu and rho square, the sampling distribution, what is sampling distribution? This is x1, the mean of the samples you're taking, right? So that will have almost, you're seeing here, right? The mean will be almost equal to the population mean. So that's why it is having population mean, but the variance will be rho square by n. N is a sample size. Okay, this single point you need to understand. Okay, we'll just come back to again this. Now, interestingly, we'll just go back and we'll see some example. Okay, so that is a theory. Okay, we'll say an example. See, let's try to investigate something. So if you just give a recap, okay, quickly. Yesterday we have created population 2 populations. We have created population 1, population 2, and we have calculated population mean. You remember this population mean, okay? And after that we have I have shown you two things. One is a sample point estimate and also the proportion point estimate. Okay. Now just with that, again go back and understand that we have this population mean. What is actual population mean? 43.00. Okay. We just took two Poisson distributions and then we have concatenated. We got population ages. Okay. Now population ages is 43.0. Okay. Are we good till this point? Did you remember this one yesterday?
Yeah, Santosh.
Okay. Fine.
Yes.
Now coming back, now see, interestingly, what will happen? First of all, if you plot that population ages, okay, this is population ages, guys. Okay. I'm showing again, this is important. Okay, population ages. Okay, if you plot, it is having two distributions. One is this distribution, population ages 1. Another one is population ages 2. You are concatenating both. Okay, it will have some mean, but if you plot this population ages, okay, if you plot this population ages, see, if you plot, I'm plotting population ages. Okay, and this is dot histogram. Okay, some bins I'm taking range from 17.5 to 75.5. Okay, you are taking the figure size. Okay, all these are fine, but mainly if you plot this, okay, see, this is a diagram. Fine, it is bimodal. Okay, it is a bimodal part. Fine, and if you see the stats.skew, you remember skew and kurtosis. Okay, stats.skew, it is having a bit of skewness. Okay, 0.1. Fine. So now if you come down, the distribution has low skewness. Okay, low skewness, because skewness is what? If you remember skewness, normality check, if I go back, skewness, okay, from minus 0.5 to 0.5 can be considered almost no skew. Remember? So it is having, sorry, it is having how much? Just 0.12 minus 0.12. Okay, that's why it is having low skewness. Okay, but the plot reveals the data is clearly not normal. Okay, it's not normal. Okay, it's bimodal. Two modes it's having. Instead of one symmetric bell curve, it is having bimodal distribution with two high density peaks. Okay, this is one density peak. This is one more density peak. Okay, the sample we draw from this population should have roughly same. Okay, so it is saying initially, okay, initially before going to the central limit theorem, it is saying if you take population, if you just take a sample, whatever the population is there, this one single sample will also tend to have the same behavior. Okay, only one sample we are seeing at a time. So see here what I'm doing, sample ages I'm creating. What is the sample ages, guys? So you remember we took sample ages. See, sample ages is what you took randomly 500 samples. Okay, you took randomly 500 samples from the population ages. Yesterday we have done this, right? So 500 ages you are taking and we are creating a sample ages. Okay, the sample ages, okay, the sample ages, if you plot, see, it is also having roughly same structure. This is population structure. This is sample. This is sample skew, and it is sample structure. See, is my point correct? Whatever the population distribution is there, the sample is also more or less having the same thing. Agree? The sample has roughly the same shape as the underlying population. This suggests that we cannot apply the techniques that assume normal distribution to this data, since it is not normal. In reality, we can thank the central limit theorem. Okay, so it is saying if you take a single distribution, single sample, okay, from this population, we took one single sample of 500, and if you plot, it will also be again similar to the original population distribution only. Then we cannot apply normal distribution properties. Okay, now he's saying central limit theorem is one of the most important results of the probability theory and serves as a foundation of many methods of statistical analysis. Okay, at a high level, the theorem states that the distribution of many sample means. Okay, here we took only one sample mean. Here, this sample ages is only one sample of 500. But the theorem says distribution of many sample means known as sampling distribution. Okay, what is sampling distribution? It is a distribution of many sample means. Okay, many sample means, the same as this. Okay, this is many sample means. Okay, the same, known as sampling distribution will be normally distributed. This rule holds even if the underlying distribution itself is not a normal distribution. Okay, that is important. Distribution of many sample means known as sampling distribution will be normally distributed. This will hold true even if the underlying distribution is not normally distributed. That is excellent point. Okay, as a result, we can treat the sample mean as if it were a, if we draw a normal distribution. Okay, the sample mean can be considered as a normal distribution. Okay, to illustrate this point, let's create 200 samples from our population and then make 200 point estimates of the mean. Okay, now this will be interesting. Okay, so if one sample, if you are taking, it is not approximating any normal distribution. It is again reflecting its own population distribution. Okay, that's why theorem is saying one sample mean will not work. Try taking many sample means. Okay, that will follow a normal distribution. Okay, that we need to do. Okay, so now what we are doing, see, same thing. So whatever we did above, to take 500 samples from the population, we are doing the same, but how many times we are doing? 200 times we are doing. Okay, that means what? For x in range of 200, okay, 200 times it will repeat, and each time what it will do, it will np dot random choice a equal to population size is 500. That means every time it will take sample 1 500 points. Okay, 500 points from population. Okay, what is the population? Population is the overall population ages population. Okay, which is like bimodal, this one. Okay, this is population. Okay, whatever the population, I am doing 200 times. First time it will take 500 samples. Okay, now S2 again, size is always 500. Okay, one more 500. Okay, like that, how many samples I'm taking, guys? 200 samples, x in range of for loop. Okay, this is sample 200. Agree? The sample 200 will also have 500 points. Okay, so total you are having 500 like that, 200 500s you are having. Agree? Is this clear how we are creating different, generating 200 samples?
Yes, sir.
Okay, so you are generating 200 samples. Fine. And after that, each time what we are doing, first time we are coming. Okay, first for sample 1, you are collecting this 500 samples. That is your sample, and you are just creating one point estimates empty list. To that empty list, what you are appending? This sample dot mean you are appending. Very simple. Come inside, take 200 samples from the overall population and just calculate the mean dot mean. You'll get some value, append it to point estimates list. Like that, come a second time, take second set of 500, calculate its mean. Okay, but this 500 will be different from this 500. Okay, there might be small overlapping, but mostly because the size is very big, there will not be much overlapping because you are taking only 500. Agree? So you are taking, assume there is no overlapping. Okay, so complete random 500 sample mean S1, append it to it. Come again, take another set of 500, calculate its mean, append. Like that, 200 times you are doing. Okay, 200th time you will come, take another set of 500, calculate its mean, append here. So now how many values will be there in this point estimate?
200 values.
Okay, fine. 200 values will have. And all those are means. All those are sample means. Okay, x2 bar, like that, x200 bar. Agree? This one. All those are this one, x1, x2, x3, whatever you are doing here, sample mean. That is the that is what we are having over in this point estimate. Okay, and what are these samples? X is 200 is what? X is 200 is this one. S1, S2, S3. These are samples that we are collecting, right? So that is this samples collection, and the mean you are calculating, right? And you are appending into point estimates. That is this x1, x2, x2 bar. Okay, so once you have that, okay, now according to our theorem, okay, according to our theorem, what it is saying, all the sample means, okay, so all the sample means we are putting in point estimate, right? So all this collection of sample means should follow a normal distribution. Okay, so as you can see when I'm plotting, okay, period data frame, okay, point estimates, okay, I'm plotting this dot plot density plot. If I do, see the graph, can you see almost like a normal distribution? Interesting. Even though the overall, see, its population distribution is not, it is in front of your eyes only. See, this is your population. You're taking, so all the samples you're collecting from where? From population ages you are collecting. And what is this population ages? This is the population ages. And what is its graph? It is not at all normal. It is completely skewed. I mean, not much skewed, but it is a bimodal. Okay. From that, you took 200 samples, and each sample size of 500, you have calculated the mean, and those mean, if you are able to plot it, you are having a almost very decent normal distribution. Okay, which is the theorem also says. Okay, I also said the same thing, right? All this will follow a normal distribution. Okay. Now see, and the sampling distribution appears to be roughly normal, despite the bimodal distribution of that the samples were drawn from. Okay, so even though the bimodal distribution of the population, still you are able to get the sampling distribution is roughly normal, not exact normal, but roughly normal. Okay. In addition to this, the mean of the sampling distribution approaches the true population mean. This is also one more point which I told you. Okay, the mean of the sampling means will follow a true population mean, that is mu. Okay, so now here also if you see this is a population mean. Okay, and this is a point estimates mean. Okay, so it is saying the mean of the sampling distribution, that means point estimates part, approaches a true population mean. Fine, it follows a true population mean. So here he is showing the difference. Approaches means if the difference is 0, they're both almost equal, right? So he's showing the population ages minus our point estimates mean. Okay, the difference you see how much it is? Minus 0.08. Okay, minus 0.08. It is almost equal, right? The difference you're able to see. Agree? It is very much equal to 0. Right? Is this clear? Are you convinced with these two statements which you have made? So I made one statement is that it will follow a normal distribution, and one more statement is it will the mean of the sample means follow a population mean. So let me know if you are convinced with these 2 points.
Yes.
Okay. Fine. So that is regarding the population. Sorry, central limit theorem, guys. Okay. And yeah, so you can think of different examples. Okay, for example, just to think of an practical example, let's say let me think, let's say in the corona time period. Okay, so when the ongoing pandemic is going on, okay, so the people are getting affected all over the world. Okay, and now if you see that corona, the actual organism, okay, the organism which has created, okay, let's say it is having some properties. Okay, let's say it is having some properties of the disease. Okay, the reason why the people were unable to create a vaccine for it is it was constantly changing, right? So for example, we were hearing that in America so many people are getting affected, China so many people are affected, India so many people are affected. Okay, so it is ongoing situation, right? So the value whatever you are going to get, if you are collecting the overall this value, it will not be a normal distribution, right? So in that scenario also, what you can do is you can just collect roughly like 50,000 people from America, 50,000 people from China, 50,000 people from India, like that, from different states. Okay, and once you have the samples, now the game is in your hands. Okay, so let's say you are collecting a specific, okay, the disease measurement of a patient's. Okay, let's say it's called corona. What shall we call corona parameter? Okay, I don't know, I'm just roughly assuming. Okay, let's say any person who got affected with corona will have some raise in RCB, red blood cells, RBC, white blood cells. Okay, something like that. Okay, I'm just assuming. And let's say they can observe one particular parameter in your body called as corona parameter, for example. Okay, now thousands of people will get affected over here. Okay, in America, China, India. Okay, so if you're able to just collect 1,000 people, okay, from America, 1,000 people from China, and 1,000 people from India. Okay. Now, these are samples. So now you can calculate the sample mean of this one, and this sample mean of China, and sample mean of India. Like that, you can do for, let's say, some 20, 30 countries. Fine. So once you have the samples, the mean of this sample means will follow what? Can you tell me? The mean of the samples means will be equal to mean of sample means will be equal to what, guys? That means I'm not saying value, it will be equal to what value?
Mean of samples,
Yeah,
population last final.
yeah. So this will be equal to the overall population mean. Okay, the mean of the samples, we see we don't know the overall population, but still, if you take sufficiently samples and if you calculate x1, x2, x3, x bar, okay, and the mean of this, just the mean of these samples will be equal to the population mean, the overall corona population, patients, corona parameter mean, whatever it is there, even though you don't know, you can just take sufficient samples, calculate sample means, and the mean of that sample mean will give you the population mean. Okay, just to give a practical example. Fine. So, but the theorem states that, and I also proved in front of your eyes. Okay, so fine. I hope it's clear. Okay, so this is a very, very important theorem, as I said, and tomorrow we are going to see some extensions and few other things on this. Okay, so but I would definitely recommend to go through this class again, guys. Okay, if it is even though if it is clear, again go through the class. Okay, because understanding central limit theorem is very, very important, because next concepts like confidence interval, confidence level, standard errors, okay, margin of error, all these are dependent on this central limit theorem only. If you don't understand central limit theorem, it will be very difficult for next classes. Okay, and again you will have something called as hypothesis testing, everything. As I said, from this level, it will be mostly dependent on the central limit theorem. Okay, and it is not that hard also. See, we do not do any derivations, equations, simple, very simple. Population, take samples, do mean of that samples. That's it. Very, very simple. Practical example also I have clearly shown you. Okay, fine. Are we good, guys?
Yes, sir.
Yeah. Okay, fine. Okay, guys. Thanks. Let's meet tomorrow.